So let us try to understand the helical milling. So in helical milling, what basically we are doing is we are generating helical gear, or you can also call it as a spiral gear. And so in order to do that, what is the requirement, what are the machining requirements, and how can that be done, and few mathematical relations is what we are going to see today. So this is a schematic which would give you an idea, a basic idea of what are the things that are required. So what you can see is this is the table, that is table on which the workpiece is mounted. And so on this table what you can see is the workpiece is held here. So this is the workpiece. Obviously this is not the exact thing how it can be held, but it's just a schematic. So the workpiece is held here. This is the job, and you can see there is a cutter here. Now the cutter, that is the axis of the cutter and the axis of the job, are at some angle. So what we can see is like this axis of the job or the workpiece and the cutter which is cutting the slots into the workpiece, they are forming an angle which would give us an angle alpha, which is nothing but the helix angle as well. But then again, when we are talking about the helix, as we already have seen, those the helical cuts that we are talking about, that is, this is the helical cut. So this helical cuts are going like this dotted line is behind the plane, so it is on the other side of the job. So basically this, the helical cuts are going along the length of the workpiece as well, not like the spur gear that it is at one position. I hope you are trying to understand what I'm trying to say. So in order to incorporate that, this cutter which is rotating, its direction of rotation is shown here, which is the material at this point of time. But as the cutter is rotating, it would be removing the material from the job. But at the same time, we also know that as we are going for the helical milling, the cutter is removing the material from the job is rotating, and at the same time the table must also move, because these helix are going along the length of the workpiece. So this is something very important. The rotation of the job must be synchronized with the table feet, the linear distance which it is traveling. Then and only then it is possible to generate the slots of this kind, which are called as the helix or the helical slots, or the helical gear which we are trying to manufacture. So again, repeating this thing because it is very important. In order to generate a helical workpiece, we are supposed to show it from the figure here. This is the slot that we are generating, this is the slot on the other side, and this is the slot we are generating likewise. So this, you can see that this slot, if I have a cutter here on this, then the workpiece must rotate in order to have the cut on one side of the circumference and on the other side of the circumference as well. And at the same time, you can see that as this cut is also moving from 0 to L in this direction, likewise here. So the table on which the workpiece is mounted should also move, and that is what is shown here. That if you want to go for a helical cut, the workpiece should rotate, which is shown by this red arrow, and at the same time the table should also move, or the workpiece should also move in a linear manner, which means that there are two motions, this one and this one. Both motions must be synchronized. If there is no synchronization, then these slots which are obtained would not be proper. Alright, so keeping these two things in mind, let us go into a bit of a detail how these things can be incorporated. What I'm trying to show here is, like, I've taken one of the helical teeth, and what I've taken is I've taken a point here, let us say point X, and corresponding to point X, what I've done is I've drawn a tangent to the helix. So this is the line which is a tangent to the helix, and I've taken the same point on the other side. I will name it as Y. These are pitch points, right? Exactly same point on the teeth or on the helix is nothing but a pitch point. So I draw a vertical from there, and when this vertical and this tangent meet, would give me some point A. And So then I can complete this triangle. There is no measurement that I've taken. I've just taken something like this, and at the intersection what I do is I stop drawing this hypotenuse of the triangle, then I draw horizontal, again I take a vertical from here, and the triangle is completed. So this distance L would give me something called as the lead of the helix. Means that when this workpiece is rotating, when the workpiece is rotating here, right, we also know that it must travel by some linear distance, which is nothing but L, and which is something that I call it as the lead of the helix. And this lead is as good as the pitch definition of pitch that we have been looking at. It is a multi-started, we call it as a lead. So this is similar to that. All right. So now that as we have been successful in drawing this triangle, what I'll do is this particular the tangent that I have drawn, it is inclined at some angle alpha to the horizontal. So this alpha would give me what we call it as the helix angle, and which is something like given here as well. So again, taking the help of the trigonometry, tan alpha is equal to pi d by L. This is how I can go for it. So like if I have been given that you want to manufacture a gear of having some alpha angle of the helix and the blank diameter is d, then what I can do is I can find the length L, or the lead of the helix, which would be important for us as we proceed with this topic. We'll try to understand what is the significance of it. So if you have understood things up to this, then I would like to introduce some two important things. That is, one of the things are the lead of the machine. And lead of the machine, again, don't look at these right now, just try to understand what do I mean by lead of the machine. So what I would require is, like, I would need some your inputs. Like, you need to be thorough with the indexing methods, and what you may come across is, like, if you could recall, we in the indexing methods what we had seen was, like, I will again try to reproduce the same thing here, a very rough diagram here. And so what we had seen was, like, if you have a job mounted here, I would write it as a job, and you have an index crank, I would put it as index crank, and you have an index plate, I put it as index plate here. I'm keeping it as fixed here. You had a gearbox. This gearbox was there, which was having a gear ratio equal to 40. Alright, and what was the significance of this? I just making you recall this. The index cranks rotate by 40 rotations. That rotations are reduced by 1 by 40 times here with the help of a gearbox having gear ratio 40, and that is how the rotations are given to the job. And this was done with the help of worm and worm wheel. Worm wheel is the one which is connected to the job, so I'll put it here, that is worm wheel is the one which is connected to the job. So uh, I'm not okay. Let us revisit the whole thing again, so that you do not get confused in understanding the helical milling here. So this is the worm that I have, a worm wheel, or the worm gear that I have, and I also have the worm here. All right. I think this would be easy to understand. So this is a part which is connected to the index crank. So this is connected to the worm. As the worm rotates, it pushes the teeth of the wheel, and so the worm wheel also rotates. This is something that we have already seen in the classes before the lockdown and at length, so I will not take much time here. But as we know, this worm wheel is having 40 teeth, and this worm wheel is connected to the job. So 40 teeth, when they are engaged, or one full rotation of the worm wheel would give one full rotation to the job. Alright, which means that 40 rotation of this index crank means one teeth, or one thread would index one teeth, and so this distance is the pitch distance that we have. So one teeth would engage the one teeth of this worm wheel. So 40 rotations of the index crank would rotate this one worm wheel by one rotation, which means that 40 rotations of the index crank would give one rotation of the job. All right, so this is something that I needed to make you revise. All right, so that means that, coming back to the helical milling, this job rotates by 40, job rotates by one rotation when the index crank is rotated by 40 rotations. All right, but then, so that reduction that I'm getting with the help of the gearbox must also be given to the table, because what I want is this rotation, whatever reduction I'm getting here, which is imparted to the job, are to be given to the table as well, because what we just saw is the table feed. This motion and the rotation both must be synchronized in order to get proper helix. Alright, so keeping that thing in mind, it is obviously, as I have been using the word time and again, the synchronize, the rotation of the job and the linear motion of the table feed must be having the same ratio by which the motion is imparted. Means the rotation motion and the linear motion must be having the same value, means they must be having the same ratio by which the motion is imparted. Now why am I talking about the ratio? It's obvious that the rotation of this would be given to the table. Now, as you have seen the milling machine, the table is having a feed rod at the bottom, so there is a significant distance between the job and the table, which is way below. So the motion from this would be transmitted to the table, which is below the feed rod, by some mechanism, and then generally that is done with the help of gears. All right, so what we need to design a gear train in order to incorporate this thing. Fine, so how do we do that? That brings me to something called as the lead of the machine. So as we just saw, the worm shaft rotates by 40 rotations, that gives one rotation to the job, and the same rotation is imparted to the table. The linear motion the table travels would be equivalent to the pitch. But as we know that there are the index crank rotates by 40 times, then the pitch would also, it should be divided, means like this 40 must be multiplied with the pitch, so that we can get the exact distance the table travels. This is nothing but it is giving us an idea about what is the distance the table travels, and this is what we call it as the lead of the machine. Alright, so it's, I think, very simple to understand. So as we know these things, I'll take a very simple example which will give you an idea exactly about what is the significance of this helical milling and the lead of the helix, the lead of the machine, and all those things. So as we just talk about the gear train, now what is it, this concept used for? It is used to design the gear train, which may be used to synchronize the motion, that is 1:1 ratio between the rotation of the job and the rotation and the linear motion of the table. So let us say this is the given data that the helical gear that I want to manufacture is having helix angle 35, number of teeth is 40, lead of the machine, lead of the helix is shown by L. Okay, it is 172 mm. So that is, let us keep it as L, capital L. It is 172 mm. This is given. Generally, there is a calculation to find this value, but right now you may study something as helical gearing in machine design, wherein you would be using the design data book to get all those values. So from that you can find this value. So I'm not going to this much that detail, those calculations, design data book. So if this data is given to me, then how can I design my gear train? So forget about this right now. The driver upon driven. So what is the driver in our case? The driver that we have here, like, try to understand when I'm talking about the driver and the driven. The driver is, let me write it here. The driver that we have is nothing but the dividing head or the index plate. Fine, that is my driver, and the driven is the job, uh, or the driven is the table, the table which is moving horizontally. Because again, I'm not going into the detail right now, but this is just the dividing head. This is a driver, and through this there would be some gear systems which would be giving motion to the table. It's something that we have already seen, so I'm not going to that detail. So then when I'm taking the ratio of the driver upon driven, obviously when we are talking about in terms of the lead, it is the inverse, right? So what I'm taking is driver upon driven is the lead of the driven upon lead of the driver. Fine. So lead of the driven, who is driven? The machine, the table. So that is why 40 into P. Generally the lead screw is, or the feed rod is having 4 TPI or 4 TPI. So generally we are taking it as 4. And L is the lead of the helix that we already want. So that is why 40 by 4 into 172. This ratio, the gear ratio, is inversely proportional to the lead. So the driver is taken in the denominator in terms of the lead, driven in terms in the numerator. So this is how we can get the ratio and the gear train, and this is the calculation that you may get after understanding the helical milling. So this is a very very brief and quick understanding of the helical milling and what are these terms. Thank you.